Sup, year 13? Right, guys. Good morning. Bright and early, Monday morning. Hello, Winkit. Right. So, that's interesting. Just going to turn my YouTube. I've popped out the chat, so I know that that's there now. Hopefully, you guys can hear me okay. Right. Do let me know if the sound quality is terrible. Got the chat popped out. Right, guys, first thing I want to do is go through your homework on acidity, and in fact, it was mostly based on copper, to be fair. But I'm going to be setting you guys transition metal homework every lesson, and I'll go through those on YouTube. I think it's worthwhile me doing. It won't take me very long. What I'm going to do is I'm going to share my screen with you guys. Go to this one. Right, then if I go to my notes and then I disable my camera, it doesn't tend to crash it. So let's see if that works. Fingers crossed. If it crashes it, I'll come back. Yes, I'm in. Amazing. Okay. Right, straight into your... So this is going to be... This lesson is Transition Metals, Aqueous Chemistry, Lesson 4. So we're going to be doing manganese today and ticking that one off the list. I haven't included my learning objectives. They're on YouTube, though. Just to include those, I always think it's quite nice to have those on my thing. So number 1 is know your colors, know manganese colors. Yeah, I'm just going to put MN colors. The MN colors, of course, there are from the table and then the oddities. Understand manganese reactions. So that will include not only the reactions that we see in the table, so with a little sodium hydroxide, excess sodium hydroxide, a little ammonia, and then excess ammonia and carbonate ions. And then the last one is to understand, what was the last one? I can't remember what the last one was on YouTube. Let me check. I think it's worthwhile me having a look at these. Edit, it'll probably tell me, yeah, manganese titrations, and that is worthwhile me having there, to be fair. Understand MN titrations. I like it. Okay, so first thing I want to do is go through the copper. So copper and acidity homework. So it says write an equation to show how aqueous chromium 3 chloride is acidic. Now the chloride bit is a trap, yeah, because in reality we know that the chloride ion doesn't do anything. And remember my sentence that you're going to hate? Everything, excuse me, everything starts off hexaaqua. Yeah, so we're going to have chromium 3+, which means it's very acidic. Yeah, there's the hexaaqua chromium 3+, and it is going to go in equilibrium. We're going to form CrH2O. This is the penta-aqua monohydroxide. Yeah, and that's going to be now a 2+ and H+. There's the acidity. And just a reminder, all 3+ transition metals are pH 3 at 1 molar, give or take. Explain why aqueous is more acidic than chromium 2+. Right, so Cr3+ has a higher charge density. Charge density. 1 mark. Higher charge density. What the chemistry? Higher charge density than Cr2+. Next, like the OH bonds in water are therefore more polarized. Now I'm just going to quickly make a point there. I'm not allowed to do that in my exam. Yeah, I would write the actual word in my exam. Yeah, therefore more polarized. And then I say therefore, third bullet point, more OH bonds. Oh, OH bonds are weaker. I'm going to change that. If they're more polarized, then the OH bonds are weaker. If you ever say that they're more polarized, you should always link that to the weakness of the bonds. OH bonds are weaker, therefore more OH bonds break. More H+. More H+ ions. We're done. It's nice to remind ourselves that any transition metal, so it's just nice for me to put, these are the nota benes, Tm3+ are pH 3, always love that. Add 2, Tm2+ are pH 5. They're less acidic. So 3 marks, guys. You're going to need all of those, by the way. So all of those will be needed. 4 ticks there for 3 marks. So if you miss any one of them, then you'll lose one. Yeah. State what is meant by the term coordinate bond. A covalent bond. I'm going to switch back to red. I don't like changing my color. Swing my pen as well. A covalent bond. A covalent bond where both electrons in bond come from one atom in the bond. It's worthwhile learning it, guys. Can I just say, by the way, if this is a question very common for transition metal aqueous chemistry. Yeah, we know this. And just to say, if it was in a context, yeah, the modification of the question would be state what is meant by the term coordinate bond in chromium hexaaqua, say. Yeah, they put you in a context. And at that point, what you say is that both electrons in the bond come from water, come from the oxygen atom in the water. Yeah, they're wanting you to give it in a context. Yeah, rather than just giving the generic one. Yeah, that's what's happening. Anyway, nice to mention that. Define the term Bronsted-Lowry acid and Lewis acid. Okay, switch back to red. A Bronsted-Lowry acid is a proton donor. I don't know what kind of accent that was. I take that back. That was terrible. Is a proton donor. Whereas a Lewis acid is an electron pair acceptor. Electron pair acceptor. Now, can I just, the reason why that's so important is because during ligand substitution, the transition metal is acting as a Lewis acid. Yeah, bear that in mind. State what is meant by the term bidentate ligand. A ligand that can donate 2 pairs of electrons to form 2 coordinate bonds. It's again coordinate bonds. Again, really important that we've got our examples in our heads. They're gonna put you in context. They're gonna ask you to give examples. Yeah, you can do the ethane dioate ion. Yeah, 1 minus, 1 minus, lone pair. So that's the ethane dioate. Yeah, dioate ion. There's also, of course, ethyl diamine. Yeah, ethyl diamine. And this one's different, of course, because the lone pairs now come from the nitrogens. Yeah. And then don't forget your hydrogens on your carbons. That important. There we go. And that's ethyl diamine. Ethyl diamine. There you go. Ethyl diamine. 2 examples of very common, most common bidentate ligands. Ethane diol, ethane 1,2 diol can also do it as well. Funnily enough, ethane 1,1 can't, which I think that's rather interesting. Right, now we're dropping into copper chemistry. Now, Edexcel loves these pathways. They love these questions where they take one thing and they move through it. And these questions are worthwhile discussing. So we're starting off with copper 2 nitrate as a solid. Now notice that it's anhydrous, so that would be white in this regard. They're going to heat it. It decomposes to form black copper oxide. You've got to know it. Yeah, I'm going to make that clearer. That's black. Oh, do you know what? I'm just going to use a highlighter here. Yeah, so black copper oxide. It's going to be white anhydrous. I mean, that's a clever thing for them to do, of course. White anhydrous. They then add it to water to form pale blue copper 2 hexaaqua. They're then going to add a few drops of sodium hydroxide, which is a pale blue, because this is aqueous. This is then, of course, going to form the pale blue solid. And then excess, which is going to be our ink blue, our dark blue at Edexcel. Dark blue solution on excess. That becomes aqueous again. On the other side, we take black copper oxide. We're going to add concentrated hydrochloric acid. We're going to form, now the observational is green at this point. Yeah, the observational is green. They will actually accept either. Yeah, this is going to be a green solution, but they will also accept yellow. If you had this, if you push the equilibrium far enough, if you added enough conc, yeah, especially since, by the way, actually, can I just point out, by the way, that they want yellow here. This is, I mean, I think that's still accepted. It's going to be interesting to look at the mark scheme. But because the reason being is we started off with a solid. This was never actually the hexaaqua. And concentrated hydrochloric acid has very little water in it. So you're much more likely to see a yellow solution. And that, of course, is going to be the copper 2 tetrachloride complex. And that's aqueous, of course. And then heating it with copper metal. We're going back to white again. I love that. And that's going to be a colorless solution. Yeah, and the reason being is it's becoming copper 1+. So one of the things I always like to do is to just, if I ever get those kind of, those cycles, it's worthwhile deconstructing them as an exercise anyway. Right, the first question, it says this is redox, so the oxidation state of nitrogen in. So we know that the copper is in a +2. So we're going to have, let's pull it apart. So we've got copper 2+ there. We've got, oh, hang on a minute. If that's copper 2+, then we've got NO3-. Right, now we can deconstruct the NO3- and work out what the nitrogen is. So we've got oxygen as a -2 times 3, which is -6. Therefore, to get from -6 to -1, the nitrogen must be bringing +5, and there's my answer. So I would have done all that working out, by the way, in the margin. Yeah, I would have done that over here. I would have kind of gone copper 2 nitrate. I would have deconstructed it over here to give me the nitrate ion and copper 2+. And then I would have deconstructed that one there. Yeah, -6, therefore +5 to get it to -1. And then it says give the oxidation of nitrogen in NO2. Well, that's a nice and easy one. Again, working out over here, deconstruct O2- times 2 gives me -4. Well, there's only one nitrogen in it and there's no overall charge. So that must be bringing +4. So +4 for the nitrogen there. So the oxidation, identify the product formed by the oxidation in the decomposition. What would be the oxidation product? It's going to be oxygen. The reason being is the oxygen is going from -2 to 0. Yeah, so the oxidation product is oxygen. The reason, explanation, is O2- going to 2. So that's going to be losing 4 electrons. Yeah, and we know that oxidation is the loss of electrons, and coming out, yeah, it means loss. So it's nice that. Nice 3 marks. So there are your 3 marks, by the way. Next, identify the state and shape of the copper-containing species in A. Right, so let's go back up to the thing. So right, so that's just for the hexaaqua ion, which is quite nice. Bog standard solution. So copper-containing species. I'm going to do it in red again, switch back to being in red. So Cu brackets H2O6, close brackets 2+, and the shape is octahedral. Yeah, and it's octahedral because we've got six ligands around it. It's nice to have the opportunity to draw it, do it in the margin. Cu, yeah, and then there we go. It's nice for me to do it as a 3D one as well. There we go. And then water, 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 water. Yeah, so octahedral around the complex due to those 6 coordinate bonds. Next, identify the pale blue species in B and write an equation or equations so B is formed from the copper-containing species A. Right, now that's so right, okay, so B, I'm assuming, is going to be the pale blue precipitate. Oh, but look, they're using ammonia. Okay, a few drops of ammonia. So the copper-containing species, of course, let's switch back to being in red here. Why not? Cu brackets H2O4 OH2. Yeah, and that's a neutral complex because we're forming a precipitate. And the equation, everything starts off hexaaqua. CuH2O6, 2+, reacting with 2 ammonias. Remember that in the littles, the number in front of that species will always match. Yeah, I'm going to form 2 NH4 pluses and Cu brackets H2O4 OH2 precipitate. And remember, just a reminder, any complex without a charge will be a precipitate. It's great rules. In what way does the NH3 behave as a Bronsted-Lowry base? Right, it's accepting a proton. The NH3 is accepting a proton. Yeah, Bronsted-Lowry. Yeah, it's going to be interesting to see if they ask that same question in the next one. I'm assuming they are. There we are. Yes. So identify the copper-containing species in C. Yeah, state the color and write an equation from its formation from B. That's clever. They're breaking the everything starts off X-rack rule. So the identity is Cu brackets. Now this is an oddity. Copper's a weirdo. When you take copper 2+, water remains above and below. Do you know what? I shouldn't do that. It's bad. It's a bad habit. Yeah, water remains at the top and the bottom, but then the ones around the middle, it's always nice to draw them as three-dimensional. There we go. And then we get ammonias slotting in around the side. And that's the dark blue. Yeah. And you just got to know these ones, guys. And that has a 2+ charge, by the way. So it's aqueous. So we've got identity. You can put the amine first if you like. Yeah. 4 brackets H2O2. There we go. And that is 2+, so it's aqueous. And that's the dark blue. So dark blue is the color. The next thing, the equation. Now, the equation is the only bit of interest for me. I think it's rather interesting because we're going from the precipitate. We're going from the precipitate, which is neutral. We're going to add, oh, that's interesting. So we're going to add, we've got no ammonias bound at the minute. So we're going to have to add 4 ammonias. And then all you have to do is just remember to kick people off. Yeah. So we're now going to form the Cu brackets, the 4 amines. Yeah, and then 2 H2Os left. And then what's going to be kicked out on the other side? So let's get rid of all this. Just all you have to do, and that is 2+, by the way, still. That now becomes 2+. Right, so what's kicked out? I'm going to kick off 2 waters, H2O2, and 2 OH minuses. And that actually cancels out the charge problem. Yeah, oh, I love one of my favorite things in A-level chemistry is conservation of electric charge. Over here, there's 0 overall charge. And on this side now, there's a 2+, but there's also now a 2-, giving me a 0 overall charge. So it's nice that I know that I'm getting that correct, which is lovely. Next, in what way does the ammonia act as a Lewis base? It is so that the ammonia is acting as a Lewis base by donating a pair of electrons. Ammonia is donating a pair of electrons to copper. We're done. Next, identify the copper-containing species in D. State the color and shape of the containing one, right? Where's D? D, okay. This is going to be really nice to check the mark scheme on this, folks, because the identity, of course, is CuCl4 2-, square brackets 2-. The color I'm going to put is yellow, but they will also accept green. Yeah, they're saying even concentrated HCl has got a small amount of water in it, but yellow is the preferred color. Yeah, we're going to see yellow. If they start off with a solid, there's no water really there. You know, there's very little in conch, so yellow's the right answer. And shape, of course, is tetrahedral. Look at that. One word for, I love that. 3 marks in 3 seconds. It's boss. If you know it, you know it. It's amazing. But I will emphasize yellow, folks, on that particular one. The oxidation state of copper in this is +1. Give the electron arrangement for copper 1+. Right, 1s2. Let's do copper normally. Element copper is number 29. So its full config is 1s2, 2s2, 2p6, back to the beginning, 3s2, skip over to the p block, 3p6, back to the beginning, 4s2, 3d9 is expected. That's not correct, though. So with copper, we have the promotion. Yeah, so we have 4s1, 3d10. There's copper metal. And then we go for copper 1+, and you remove the 4s1. So there's my final answer. 3p6, 3d10. Deduce the role of copper. So number 1 is going to be colors, by the way. Yeah, because it's got a full D subshell. Therefore, electrons cannot become excited. Therefore, they cannot absorb visible light. Therefore, all is reflected. Deduce the role of the copper metal. It's a reducing agent. I think that's genius. The reason why it's a reducing agent is because we're going in the cycle Yeah, we're going from copper 2+ here, and we're going to copper 1+. Now, we know that when on the redox ladder, I love the redox ladder. Yeah, the redox ladder is such a useful tool, and the middle is 0. And if you climb the ladder, you're being oxidized and you're becoming more positive. If you're coming down the ladder, you're being reduced in charge. Yes, this one's being oxidized. So what's happening here is it's actually going from 2+, I'll change my color, it's going from 2+ to 1+. It's being reduced. So the copper metal is acting as a reducing agent, which is really nice. If you actually write the equation for that, you can even see that it's actually disproportionation. Yet the Cu metal is a reducing agent. Hardest question on the sheet probably by a mile. Yeah, copper metal, Cu metal is a reducing agent. A red agent. I'm just going to put red agent. I know you know what it means. And we're done. It's out of 7, is that out of 17 marks in total? I believe it is, because it was only one question from a paper. Oh, no, there were others. Right, so hang on a minute. So the total number of marks, 3, that's 6, 7, 8, 7, 8, 9, 10. Yeah, so 17 for question number, that for the latter question, 10. But then this one was out of 3, and then 6 more, so it's out of 9. So the total was 9 plus 17, so it's out of 26. And you can actually add your score to the sheet now, guys. That would be really great. So score sheet, that was out of 26. What a great score. I like that. 17 and 9. So you can add your scores now, guys, to that sheet. That would be grand. Oh, I don't want it to do that. There we go. Be lovely to see how you got on with that. Yeah, I put green too. How about green instead of yellow? You can have it today, guys, but it'd actually be quite nice to see which exam paper I got that from and to see if I'm pretty sure they'll accept it. But it is always nice to confirm, isn't it? 23 for Julian, well done. If I go back to my notes and find out which question it was that I stole this from, it's quite a famous one with that particular thing, and it was question number 10. I bet if I actually... I got it from PMT, definitely. PMT. Yeah. See if I can track it down. I didn't have to spend an awful lot of time trying to find them. They're so common that it's just pretty easy to do. So unit 5. Oh, look, see, I haven't chosen many. Right, okay, there's a couple. So let's have a look. Let's start from the top, I guess. Sure, why not? Let's have a look at 2011. And see if I can see the section on. There's so many, though. It's so easy. There's a manganese appearing, which is today's lesson. Manganese all over the place. Oh, which one's that one? There's a chromium set of colors. Chances are, if they've just done a chromium, then they're not going to do a copper. Let's go for the next one. Let's go for 2019. I don't think it was the 2015. It's not going to take me very long to find it, folks. And once I've found it, I'll just quickly go to the mark scheme on it. It's worthwhile me taking the time for this, just to kind of make you feel better. It doesn't look like there's loads of copper there, but it's not a cycle. Let's go to the next one. Let's go to 2016. Just going to the ones that are highlighted. See, these are the ones that I've used in the past. So I'm assuming that's where it's going to come from. Come on, give me the cycle, will you? Manganese reappear. Oh, look, more manganese. Love manganese. There's chromium appearing. Where's copper? Oh, it's going to be really unlucky for me not to hit that. Not to be able to hit the thing immediately. Let's try the 2017 paper. Come on, be nice to me at Excel. Oh, there's a chromium question. Come on, be nice. Give me my cycle. Oh, is it going to be the most recent? Could be. Have I just skipped 17? It's possible. I'm going a bit too quick. That's one of my problems. Oh, organic prep, we need to work on that one. I can't track it down. It's going to really bug me, that is. I wouldn't worry about it, folks. I don't want to spend too long trying to find a mark scheme for a question. If somebody fancies finding that, you can, if you just Google the entire question, as in like if you Google bits of it, it'll come up and then you'll be able to check it, but they'll allow green on that particular one. I was figured that I didn't. Look at that. What a great set of scores. Well done, guys. Really, really pleased. Right, let's move on to manganese today, folks. Let's move on to manganese. Right, today's lesson. Manganese. There we go. Manganese. Okay, so manganese, let's check it out on the periodic table. Where are you, manganese? Now, manganese is an important one, guys, for you guys to know, because manganese is, there we go, number 25, just before iron. Now, the first thing I want to do is let's do manganese in terms of its colors for the table. So let's go manganese. Trying to just give myself a bit more space. Manganese. Okay, so what we're going to do is we're going to look at manganese 2+. So the most common oxidation state for manganese when you're doing aqueous chemistry is manganese 2+. And what that means is its pH is approximately 5. So what we're now going to do, let's put manganese in our beautiful manganese love heart. So we're going to start off with something like manganese 2 chloride. Yeah, we're going to start off by inputting into this particular scenario MnCl2. Yeah, it's a colorless solid. Yeah, because it's anhydrous. Yeah, a colorless solid, and you can write colorless underneath there or on top of it, as I've just done. So colorless, we're going to add that to it, and the first thing we're going to do is we're going to add water to this. Yeah, so the first thing that we come across is when we add water, add H2O. The first thing you're going to form is the manganese hexa-aqua ion, hexa-aqua manganese 2 complex. Now this one's an awkward one. The reason being is it is pale pink. Like so pale pink that it's basically colorless. That's the color it is. And they allow both. I actually prefer you to learn colorless. It's a pale pink color, pale pink, but in reality, observational, it's colorless. You can't, it's so pale, you can't see it. If you put it on a colorimeter, you'll see its color in a spike. But in reality, to the human eye, it's colorless. And I actually want you to learn that one. It's kind of learn colorless for it. Yeah, but don't be surprised if in a question they talk about it being pale pink. That's what I need you to be able to do. Okay, so practical number 1, we're going to add a little sodium hydroxide, OH-. Yeah, a little, and the reagent, nice to mention reagents, a little OH-. Now, as soon as you do that, you're going to form a brown, no, it is a brown precipitate. It is. It's kind of gross. Brown precipitate. Yeah, it's a pale brown precipitate. So I'm doing copper. It's a pale brown precipitate of this guy. It's pale brown. And it's neutral. There's no charge. The reason being is I've put the 2 inside the bracket. It's really easy to do, isn't it? Blimey, so easy. There we go. That's better. So the Mn2+ is being, the charge on the Mn2+ is being cancelled out by the 2 OH- ions that are now attached to it. And this is a pale brown precipitate. It'd be nice for me to check that color, actually. I do just want to make a check of that. It's because one thing I need you guys to realize is it darkens on standing. So we need to know that one. So if we go manganese, sodium hydroxide. Let's try that. See what that does. Sodium hydroxide. Sure, let's just do hydroxide. Go. There you go. So it forms a pale brown. Now, what do they call it? They don't actually call it anything. Oh, that's quite funny. Oh, that's entertaining. They don't actually give it its color. Oh, is it there? Hello, manganese. That doesn't help me at all. Well done. Stupid internet. It's pale brown. I think they actually will just accept brown, by the way. But I prefer pale brown. The reason why is because it changes color on standing. So it's a pale brown. See if I can find a pale brown. Yeah, I'm going to go for like that kind of color. There we go. So it forms a pale brown PPT. Pale brown, PPT. Gone Yorkshire. Oh no. Right, so now key thing here is that one don't change. And right, and I know you're not going to like that, are you? You're going to be like, hang on a second, you just said it darkens on standing. Now it doesn't darken on standing in that scenario. But if we go to excess, let's go to excess sodium hydroxide. Now what happens is you form exactly the same complex. Now the reason why is because it's a 2+, which means it's not acidic enough. Yeah, it will form the same thing. Yeah, it's a solid. It forms the same precipitate. And the reason being is because it's not acidic enough. If you've got a transition metal of 3+, they like to redissolve. Iron 3+ being an exception. It's iron 3+ actually isn't an exception. It does redissolve, just not very much. But this does not, it doesn't redissolve because it can't go to the extra one. It can't lose another one, become a 1- ion because it's not acidic enough. Now this one, now on standing, yeah, it actually oxidizes. It forms MnH2O3 OH3, which is still a precipitate, and it's dark brown. Yeah, that's what I mean by, it's better to say pale brown at the beginning because there can be a distinguish them. You can actually say brown and then dark brown. So it forms a pale brown at the beginning. It says pale brown. And then it forms a dark brown on standing. Dark brown. Right. So let's just write the equation for what's happening there. We have got Mn, we've got the, now students, first of all, let's do the equation, and then I'm going to explain why it doesn't do it originally. Yeah, there we go. So this is a precipitate. It reacts with oxygen. And what I'm going to do is form a 3+ complex, MnH2O3 OH3. Now that Mn in this stage is in a +2 oxidation state, and over here it's in a +3 oxidation state. And what's going to happen is the oxygen is going to form water and be reduced. Now we need to balance it. So here's what's happening. The oxygen is kind of stealing a proton and then, of course, oxidizing it. So there's still no overall charge. Let's divide this into the two half equations, just for entertainment purposes. Yeah, let's just split this into the half equations. So if I go from that to this, now there definitely is now a change in oxidation state. So of course, in reality, the only thing that's actually moved from here to here is the loss of a proton. So I'm going to spit out a proton on that side. Now, if I spit out a proton, on this side, the overall charge is 0. But now on this side, the overall charge is +1. That can't be correct. We need to balance it with an electron. Right, now that adds up. There's the half equation for the oxidation process. What's then happening is the oxygen, of course, forms water. We can balance that half equation. Yeah, let's do it with a half O2. Yeah, and then I need 2 H pluses and then 2 electrons on that side. Right, I can now double the top equation times by 2. Yeah, so I end up, because I need the electrons to cancel. So 2, 2, 2, and 2. And look what now happens, of course. Cancels, cancels, cancels. Oh, cancels. Nice. So since that all cancels, all I actually need to do is do a 2 there, half in front of that guy, a 2 in front of that one, and then a 1 in front of the water. And that now all adds up. And there are no spare electrons since there's no actual overall charge in these equations originally, because there's no charge here and no charge here. So 0. No charge here, no charge here. Makes sense. That's why the H pluses and the electrons both cancel out. Nice that. Hard equation though, right? Can I just point out the knowledge that you must learn there is that oxygen always forms water. And that's a great rule for redox. Keep it. It's worthwhile keeping. Oh, suddenly realized that I've managed to get rid of my chat window. So for, okay, sorry, Dixon's asked me, so for hexa aqua manganese, can I write pale pink close to colorless. Sure, they'll allow it, Dixon. They would allow that. Yeah, they would allow that, the fact that you've given both. Absolutely. Yeah. Right. So the next question is, why doesn't it oxidize in the little? The reason being is, if you remember my previous lesson, if we want to this is a nota bene. Nota bene. Got to say with an Italian accent, you see, even though it's Latin. Nota bene, important notice. So we remember that if you want to oxidize, yeah, if you want to oxidize a transition metal ion, yeah, then you need the conditions, and the conditions and the reagent. The reagent is hydrogen peroxide, and the condition is alkali. The condition is alkali. Now, what that means is that even though our oxidizing agent in this case is oxygen from the atmosphere, yeah, this is our oxy agent, we still need the alkali conditions to do it. Now, what this does tend to mean, by the way, that if you ever make up a transition metal solution, you should always just make it an acid. If you make it a slightly acidic, you'll prevent it being oxidized. Anyway, so because it needs to be alkali, now when it's in a few drops, the OH minus ions are all taken up acting as a base and they're not in excess. What that means is the condition is actually neutral because it's being neutralized by the transition metal because it's being acidic. Whereas once we go to excess, we're now left in alkalized conditions and it will oxidize in air. Really clever chemistry. Right, next. Now then, one of the next ones, of course, I love this particular strand. We're now going to do ammonia and we're going to do little. Now, the great thing is we always remember that the littles are always the same. So I'm going to form the same brown precipitate that I did previously. Yeah, I'm going to form the same thing, as the two littles are always the same. This is handy. Learn it. Makes my life so much easier. Yeah, these two here are always, that's not very helpful. These two here are always the same. Yeah, littles are always the same. This is nice. And the reason why is because the ammonia is acting, ammonia role is a Bronsted-Lowry base. It is removing a H+. Yeah, Mn2+ has the water molecules, 6 of them bound to it. And in this case, the ammonia is acting as a Bronsted-Lowry base because it's taking a proton. Yeah, so we've got proton transfer going on. And then we get the excess. Now, in this particular scenario, the great thing is about manganese is that there's actually no difference at all. So manganese flat out refuses to go through any substitutions. Just to show you that it was down here on standing. It does exactly the same thing as they don't give. I wonder if any of them actually gives any more details on the fact that it doesn't do it. I don't think so. It's annoying, the fact that it doesn't do it. But yeah, so essentially manganese, of course, doesn't actually do any swap out at all with ammonia, which is very common for a 2+. Iron 2+ does exactly the same thing. It's not able to act, it's not a good enough, the charge density of the metal ion, because it's a 2+, is not dense enough to be able to pull, because, okay, I'll write the equation down. So the first thing is, what we're going to form here is exactly the same thing. And guess what it will do on standing? It does the same thing. Yeah, guess what? So it forms again the same pale brown precipitate, even with excess ammonia. Yeah, excess ammonia. Yeah, and then it will do exactly the same thing that the previous one did. It will oxidize on standing. This is where I need to, I've run out of space. I need to move the whole thing. Just swing that over to there. That'll be better. There we go. Gives me a little bit more room. So yeah, and it does exactly the same thing. Darkens on standing because it's now in alkali conditions. So the key thing here is to remember that manganese does no swapping at all with ammonia. It's not a good enough, it's not a high enough charge density to be able to, for the ammonia to act as a ligand. That's all. Yeah, I know that seems odd. Sorry. There we go. Oxidizes again on standing because it once again is in an alkali condition. But no subbing out. The next thing is what would happen in terms of the carbonate, and the rule still applies. Yeah, if you add carbonate ions to this, yeah, you're going to form magnesium carbonate. Just to show you what that looks like. Manganese carbonate. Manganese carbonate. Go. There we go. And once again, pale brown. It's quite nice, just that they kind of, it's almost a pinkish color or a flesh-like color, but they just want another pale brown. Manganese is a nice one. I know that the internet's a great resource and giving us all kinds of different colors there, and it's a bit of a nightmare. But yeah, it forms a pale brown precipitate. Oh, it's nice. Look at that. Rhodochrosite. I've never heard of that. It's weird. So once again, pale brown precipitate is the carbonate. All 2 pluses form the carbonate. Right. So now that we've gone through its table chemistry, yeah, what we can now do is add on the oddities. So oddities for manganese. Okay, so oddities for manganese, potassium permanganate. We need to know this guy. So potassium permanganate is dark, dark, dark purple. The color is that, dark purple. This is where what I now need to do is I need to draw the dark purple first and then replace it with white text. Yeah. Potassium permanganate is a dark purple solid. Now, can I just point out, as a solid, it's so dark purple, it's borderline black. Yeah, in reality. So when you add that to solution, when you add to water, yeah, add to water, add H2O, you will form a dark purple solution. Yeah, so this just becomes aqueous. Exactly the same thing again. KMNO4, yeah, aqueous. Now, just to tell you which ion is causing it, and this is the important bit in reality, yeah, the ion which is causing it is that we have K+, which of course is colorless because it's not a transition metal, but what of course we have is the purple MnO4- ion. Yeah, MnO4-. Right, and that's aqueous. Okay, so those are actually, no, there is one more color that you need, which is the oddity. So this comes into the titrations using potassium permanganate. So if, I'm trying to think of the best time at when this appears. It's during the reduction of it. So when you do so potassium permanganate is an oxidizing agent. So we can just do potassium permanganate titrations. Titrations. Number 1, facts. Let's do some facts. I know I don't have very long now, guys. Facts. Number 1, KMNO4 cannot, underline it, cannot be used in transition metal titrations if Cl- or Br- ions are present. Now, the reason why is because potassium permanganate is a powerful oxidizing agent. Yeah? And what it would do, so explanation, reason, is because it'll oxidize the chloride ion up to chlorine. 2 electrons. And you'll form chlorine gas. Same with bromide. Yeah, it'll oxidize them. Don't really want to fill a chemistry lab with chlorine gas or bromine gas. Now, what that will do is, so if you have that happen, what that means is you're tighter, so the amount of potassium permanganate will increase, tighter to large. I'll explain that now. So fact number 2, potassium permanganate is commonly used with iron. So KMNO4 is often used often used to determine Fe2 plus concentration. The reason being is the potassium permanganate, is going to itself be reduced to Mn2 plus, balance the half equation, plus 4 H2Os. I'm just running them away, by the way. There we go. Plus 8 H pluses, plus 5, plus 6 electrons. There we go. So the potassium permanganate is being reduced, and the iron 2 plus is oxidized to Fe3 plus 1E minus. And then when you put those two together, you have to multiply this one by 6. So what we realize is that the potassium permanganate can be used in a titration with iron 2 plus. It's very effective. And the great thing is there's an easy color change because there's no indicator needed, because the potassium manganate is going from a dark purple to pale pink to the point where it's colorless. But then when the MnO4 minus goes into excess, have I just made a mistake? MnO4 minus 7, it's 5 electrons. Sorry, thanks. Did anyone mention it? Nope. So sorry guys, I forgot my ion charge. So easy. So the potassium permanganate starts off as a dark purple, and then turns colorless when it hits the MnO4 minus. It hits the iron 2 plus, turns itself into Mn2 plus, which is colorless, and then the iron 2 plus goes from green to yellow. Now the indicator actually is not needed because the potassium permanganate, when it goes into excess, goes purple again. So by the way, end point, and this is a nota bene, by the way, because they ask this a lot. End point of KMNO4 titration is colorless to pink. And the reason why is because you're adding dark purple potassium permanganate. You're adding dark purple potassium permanganate into your iron 2 plus. Into your iron 2 plus solution, which is so pale green you can't really see it. And of course, as soon as the purple color hits it, it becomes colorless. And it will keep doing that until eventually, you keep adding the purple. Whoops, I added too much to there. Keep adding the purple until eventually what happens is the potassium permanganate goes into excess and you get a purple drop, doesn't go colorless, and so the whole thing turns a pale pink. The whole thing turns a pale pink and you know when to stop because the potassium permanganate is now in excess. It's clever game, actually. So now, just to let you know that we say it's too large because if there was a chloride ion present, what would also be happening is a second equation, which is you'd be needing electrons for the chloride oxidation process as well, which means you're going to need more electrons, you're going to need more potassium permanganate. So this second equation means that the titer is going to be too large. Too large, because we're having to use extra to be able to oxidize the chloride ions. Okay, so we can't use it in the presence of chloride or bromide ions. So the acid we'd have to pick, by the way, to acidify this, because it needs to be in acidic conditions. We're going to use dilute sulfuric acid to acidify it. Can't use hydrochloric acid because it'll oxidize it. Now, the next thing is, what's the extra color? So the extra color is the fact that if you do this and you don't add enough acid, an awkward bit happens, which is what you'll form is, what's the best way of doing this? If you add a reducing agent, like zinc, they've done this. I want to have a look at the question because the question does this properly. They actually give a really good example of when this other complex forms, which is over here. There we go. So on standing with air, on standing with air, but the thing is, air is an oxidizing agent. Yeah, but it just does. It shouldn't do that. Oh, hang on. Mn2 plus. Oh, they're oxidizing it. Okay. Sorry. That makes more sense. I've realized my lesson's come to an end. Yeah, you guys can leave and then watch it back to finish. So if once you've got to Mn2+, yeah, if you leave this to stand on air, what will happen is you'll form MnO2 dot XH2O. You'll form manganese dioxide in a hydrated form. And that there is brown, I believe. Manganese dioxide is black. That's what it is. It's black. And then you can drive it back into manganese oxide as well. What I'm going to do is I'm going to leave you here, guys. I've overshot my time. So I'm going to end it there. But then what I will do is I'm going to send you the homework of this manganese question, and then I'll explain it in the next lesson. So I'll end it there. We'll do a manganese part 2 at the beginning. Right, let's go back to here. I've got to go to my notes, then activate my camera. Enable device. Don't crash. Hey. Right, and then I can go back to StreamYard. And then I can turn my camera on. It should give me the front facing. Yay. Right, guys, I'll leave you be at that point. I hope you found it useful. I will see you guys next lesson, and I will go through the manganese homework. You've got a chromium one to do as well. 2. All right, guys, I'll see you soon.